Hi guys, क्या हाल चाल है भाई? Hello everybody, how are you guys doing? I have a little allergy issues today, and that's the reason I have to have a bit of coffee in the morning. Um, I hope you're doing good. I hope you are enjoying yourselves, keeping yourselves healthy, safe, everything. Like everything is going nice with you guys, and welcome back to the Catalysis channel of Vedantu, and this is Saurav Goswami, and we are doing coordination compounds, and we are at lecture 5, if I'm not wrong. We're at lecture 5, and in this lecture 5 we would be discussing about the effective atomic number. Okay, we'll be discussing about effective atomic number. Okay, so chalo, let's start today's session. Let's start today's session, and let's start our session with the with this idea that in the last class, if I'm not wrong, I had given you a homework problem. Okay, I had given you a homework problem, and the homework problem was the answers to that homework problem were given by few people, and I have collated the names of these people, and so let's see. The question was this. The question was this. If I'm not wrong, the question was this. The question was the IUPAC name of CONH36 CrCN6. Now, first and foremost, you need to know that NH3 would not contribute to the oxidation state, and Cn would contribute to the oxidation state. So minus 6 charge, I will divide plus 3 uniformly on cobalt and chromium. So if I start naming this part, you see that both the parts, the cationic part and the anionic part, both of them are in the form of a complex species. Both of them are in the form of a complex species. And so if I start naming this part, I will name it as hexaamine cobalt 3, and then hexacyanochromate 3. Why I would not write cobalt 8 is because cobalt is a part of cationic coordination sphere. I'm sorry guys. Cobalt is a part of cationic coordination sphere. So if it is a part of the cationic coordination sphere, the name would not be changed. Okay, name would not be changed. I hope this is clear to you guys. The right answer for this question would be A. The right answer for this question would be A. Everything else is incorrect, and the right answer was given by, I have taken 5 names as opposed to 3 names that I told you. Vinay Kiran, he's from Hyderabad. Vivek Vikas Chakravarti, he's from Siliguri, West Bengal. Aarti R from Tamil Nadu. Akanksha from Delhi. And Muralidhar comes from Raghunathpur, in the district Purulia of West Bengal. In fact, Raghunathpur is famous for, if I'm not wrong, the there's a kind of a jewelry industry that is well placed at Raghunathpur. If I am not mistaken. So Muralidhar, please do tell me in the comment section that if I'm right or wrong, because this I recall about Purulia, that Raghunathpur and Purulia has if I'm not wrong, a jewelry industry around there. Is NIT Rourkela good? Yeah man, NIT Rourkela is good. EC is good. Okay, so let's start today's session, and we're supposed to discuss effective atomic number. What is effective atomic number? What is the purpose of effective atomic number? We'll discuss it today. So what is effective atomic number? In fact, when people started identifying complexes, so when Werner completed his work and people started identifying more and more complexes, they tried to suggest a certain way to make sure that the compounds that they are discovering are stable compounds. Okay, so when they were discovering certain compounds, they tried to give a non-empirical means non-experimental rule to suggest how can compounds become stable. So there was no octet rule. They tried to create a type of octet rule. See, octet rule is again a non-empirical rule. The octet rule says that you need to have 8 electrons in the valence shell. So over here, what they said is, since we do not have an octet rule for elements which are forming complexes, primarily the D block elements, so let's create a rule for them so that if they abide by these rules, then these complexes will be stable, and if they do not abide by these rules, the complex will be unstable. Okay. So how does it work? So effective atomic number is calculated in a very simple manner. Effective atomic number is calculated by taking into consideration the atomic number of the central metal atom or the central metal ion. You remove a certain number of electrons from there depending on the oxidation state. If the oxidation state is +3, you remove 3 electrons. If the oxidation state is +6, you remove 6 electrons. Depending on the number of oxidation, depending on the oxidation state, you remove certain number of electrons and you add as many electrons as many as possible depending on the number of ligands that you are binding with. So if you are binding a monodentate ligand, you will multiply the number of electrons that are donated by monodentate ligands by 2. Okay, if it is a bidentate ligand, then for every bidentate ligand 4 electrons will be donated. For every tridentate ligand will donate 6 electrons. Okay, every tridentate ligand will donate 6 electrons. Okay, so let's see the application of these rules. Let's take a complex, the Werner complex. If you recall, CrNH36 Cl3. Now the central metal atom is chromium. Chromium's atomic number is 24. Okay, so chromium's atomic number is 24. The oxidation state the oxidation state of chromium is +3. Okay, oxidation state of chromium is +3. So I will remove 3 electrons. Clear? So scandium, titanium, vanadium, chromium, 24 is the atomic number. The oxidation state is +3. You remove 3 electrons, and then there are 6 monodentate ligands. So for 6 monodentate ligands, you will add 2 electrons each. So that will result in 21 plus 12. 21 plus 12 turns out to be 33. 21 plus 12 turns out to be 33. Is that clear? Is that clear? Any doubt? Is that clear? So it turns out to be 33. Let's take another example. K4 FeCN6. Iron's atomic number is 26. Oxidation state is +2. So you remove 2 electrons. You remove 2 electrons. And then you add a total of 12 electrons, because you can see that there are 6 ligands. Okay, there are 6 ligands. So it becomes 24 plus 12, that is 36. Now there are two numbers that you're getting, 36 and 33. According to the person who has pronounced this effective atomic number rule. Effective atomic number rule was given by Sedgwick. Okay, it was given by Sedgwick. According to Sedgwick, any element which has the effective atomic number of the noble gas which appears in that period. So in the fourth period, the noble gas that appears is krypton. In the fifth period, the noble gas that appears is krypton, xenon, okay, and sixth period, the noble gas that appears is radon. Okay, so helium, neon, argon, krypton, xenon, radon. Clear? These are the noble gases that appear in fifth period, sixth period, and fourth period, fifth period, and sixth period. Now in fourth period means the 3D series. Fifth period means the 4D series, and sixth period means the 5D series. What is the atomic number of what is the atomic number of krypton? Atomic number of krypton is 36. What is the atomic number for xenon? Xenon is 54. And radon, add 32 to it, so you will get 86. So if your metal belongs to the 3D series or the fourth period and its effective atomic number turns out to be this value, then according to Sedgwick, that complex is stable. If the element belongs to fifth period and the effective atomic number turns out to be 54, then it is considered to be stable. So on and so forth for the sixth period. Is that clear? Is that understood? Please tell me a yes if you have understood this. Please tell me a yes if you have understood this. Please tell me a yes if you have understood this. That what is the significance of effective atomic number, how to calculate effective atomic number, and what is the value of effective atomic number that I should be looking for. Is that clear? Akansha says yes. Everybody else, please tell me. Hello Vidhi, you're class 10th student. If you're in class 10th, you can stay, but I don't know how much you will be able to understand. Chalo. Clear? Lovely. Let's look at the effective atomic number of certain complexes. Okay. Clear? Chalo. Let's look at effective atomic number of K4FeCN6. So if I take K4FeCN6, iron's effective atomic number turns out to be 36. If I take NH3 it should be NH36, sorry, it should be NH36. So CONH36. So I did calculate the K4FeCN6, potassium hexacyanoferrate 2. The next one is CONH3 6Cl3. So cobalt is 27. Atomic number for cobalt is 27. And we remove 3 electrons and we add 12. So it turns out to be how much? 36. If I take NiCO4, Ni has atomic number of 28, and so 28 CO, absolutely no reason we have to assign oxidation state, that's like no reason like we should assign a positive oxidation state. The oxidation state over here is 0, so this will be 0 plus 4 monodentate ligands, so they will be assigning 8 electrons, so that will turn out to be how much? The 28 plus 8, 36. Okay, if I take K2PtCl6, now platinum's atomic number is 78. Okay, and platinum has an oxidation state of +4. You can see that -6 +2 +4. So this is remove 4 electrons and add 12. So 74 plus 12, that is 86. Okay, this should be Rn. So this has a E.A.N of. So according to Sedgwick, these complexes are more stable. Okay, but there was a major flaw. There was a major flaw that if I take a complex like K3FeCN6, potassium hexacyanoferrate 3, then the effective atomic number for this turns out to be 26 minus 3 plus 12. So this turns out to be 35. This turns out to be 35. If this turns out to be 35, according to Sedgwick, this should not be stable, but it is quite stable. It is quite stable. Potassium hexacyanoferrate 3 is quite stable. Similarly, the previous example where it was not turning out to be 36 is quite stable. So effective atomic number is now an obsolete rule except for metal carbonyls. Please do remember, except for metal carbonyls. Metal carbonyls will follow it religiously, and a number of properties of metal carbonyls can be predicted using the effective atomic number rule. Okay, man, at least for first 30 elements you need to remember them. For the first 30 elements you need to remember the atomic numbers. Okay, chalo. So let's look at certain features of metal carbonyls when we try to use effective atomic number on them. Okay, let's try to look at certain features of metal carbonyls when we try to use effective atomic number on them. So let's say we take a complex like VCO6. Okay, VCO6. This is the only exception name. There are a lot of exceptions. Okay, I would say that do not call them exceptions. This is not a very this is not a law. Okay, this is not a law. So there can be like deviations. Rather than calling them exceptions, call them deviations. Okay. So VCO6. Now let's look at what is the atomic number of vanadium. Vanadium is 23. And CO is a monodentate ligand. So it will turn out to be 12 electron donation. Effective atomic number is 35. Is everybody getting the effective atomic number of VCO6 as 35? Or is there anybody who is getting a different effective atomic number for VCO6? Is everybody getting the effective atomic number of VCO6 as 35? Please tell me in the chat box if everybody is getting the effective atomic number of VCO6 as 35. Yes, is everybody getting it as 35? Chalo. So if everybody is getting it as 35, now if I say that something follows the rule religiously, it means the rule is being followed to the, like, by the line. Like if it is written that it has to have an effective atomic number of vanadium is present in the fourth period, so it should have an effective atomic number of 36. It will want to achieve it. It will want to achieve the 36 effective atomic number. Okay, it will want to achieve the 36 effective atomic number. So why, and or sorry, what would be the property of VCO6? If I ask you if I ask you that what will be the property of VCO6, the property of VCO6 will be that it will behave as a oxidizing agent. Why it will behave as an oxidizing agent? Why it will behave as an oxidizing agent? The reason it will behave as an oxidizing agent is that to acquire the effective atomic number of 36, it needs one more electron. It needs one more electron. Only then it will become 36. And how will it take one more electron? By oxidizing something and reducing itself. So VCO6 will take up an electron and will turn into VCO6 minus. So VCO6, if you are being asked that what is the property, will it behave as an oxidizing agent or will it behave as a reducing agent? You have to say that it will try to achieve this effective atomic number of 36 by taking an electron. Clear? On the other hand, if I take, suppose I take MnCO6. If MnCO6 is taken, then MnCO6, Mn will be 25 plus 12, that will be 37. If it has to abide by the effective atomic number rule, what do you think will be the behavior of MnCO6? Will it behave as an oxidizing agent or will it behave as a reducing agent? You have to remember that oxidizing agents oxidize something else and take up an electron and reduce themselves. Reducing agents are the ones which give an electron and oxidize themselves. So what will be the right answer over here? Will it behave as an oxidizing agent or will it behave as a, very good Akanksha, it will behave as a reducing agent. It will behave as a reducing agent. And why will it behave as a reducing agent? Because it will want to lose an electron to become 36. Okay, so this process, okay, the conversion of this into MnCO6 plus is a favorable one. You could be asked a question that conversion of VCO6 to VCO6 minus is a spontaneous or non-spontaneous, favorable or non-favorable. So you will have to answer that it is favorable. Clear? I hope this is clear to you guys. Okay. Pardon me, I'm like a little unwell today. And this keeps happening when it rains in Bangalore. So it's been raining since yesterday night. So My allergies issues just keep cropping up. Okay, chalo. Let's move on to the next thing. So let's take some questions. Okay, let's take some questions. Fine, let's take some questions. So let's start with the first one, and let's start with something that we had done in the last class. Okay, let's start with something that we had done in the last class, and that was IUPAC naming. Okay, that was IUPAC naming. Anyways, I'd like to point out that QWERTY did reply. He was the third quickest in replying to the homework question, but I had to exclude him. Jack, I had to exclude you because the nomenclature depends on how correctly you write the name. Your name had spelling mistakes, man. Okay. Chalo. Let's start with this. What is the IUPAC name of this complex? So, oxidation state of both the nickel will be 2 and 2. So, the name would be tetraamine nickel 2. Both of them are complex spheres. The names would be tetraamine nickel 2, tetrachloro nickelate 2. The right answer. Hello, Vaishnavi. Okay. Tetraamine nickel 2 and tetrachloronickelate 2. Clear? I hope. B is incorrect, man, because this nickel is a part of anionic coordination sphere. Anionic coordination sphere. So it should be nickelate. It should be nickelate. Clear? The answer should be C. Answer should be C. Let's move on to the next question. The IUPAC name of this complex. The IUPAC name of this complex. So please do remember cation, anion. Whenever you name a complex, always start with ligand and then go to metal. When you come to ligands, you have to always name them alphabetically. So you have, what do you think will be the right answer? What do you think will be the right answer to this question? Deva, incorrect. The right answer is given by Akanksha. The first right answer is given by Akanksha, then by Sri Balaji, then Bhanu Prakash. The right answer is pentaamine nitro cobalt 3 chloride. Pentaamine nitro cobalt 3 chloride, because this is amine, this is nitro, and this is cobalt. Oxidation state -1 and -1 over here, and there would be a total of 2 chloride ions, so -2 -1, so that makes up +3. Okay, the right answer is A. Okay, the right answer is A. I hope this is clear to everybody. The right answer is A. Okay. So let's move on to the next question. The IUPAC name of this compound? CONH3 whole thrice H2O 2 Cl, completely in the bracket, and outside the coordination sphere there are two chloride units. Okay, yeah, nitroso is NO beta. Okay, so what do you think will be the right answer? Which will come first? The right answer will be yes. The right answer will be B. Yes, correct. Right answer will be B. And Diva has given the right answer for the first time. Among everybody who is here, she is the fastest. And NH3 is amine, AMMINE, and H2O is aqua. Okay, so A alike, and then M, and this is Q. So M comes before Q. Okay, sorry. So triamine, diaqua, cobalt 3 chloride. Diaqua chloro cobalt 3 chloride. The right answer should be B. Yes, exactly. Correct. The options are pretty easy. You can do it by elimination. Okay, you can do it by simple elimination. The right answer is B. Next, chalo. Let's move on to this question. What is the effective atomic number of cobalt in the complex? We just did this question, so this should not be difficult. What is the effective atomic number of cobalt in this complex? Yes, amine is a neutral molecule. NH3 amine ligand or ammonia is a neutral molecule. Answer should be Alan Walker has given the right answer. The first one to give the right answer is Alan. So it is 36. Pretty easy a question. Cobalt is 27. Oxidation state is +3. So I remove 3 electrons. And 12 comes from NH3. So this becomes 36. This becomes clear? I think it is clear to everybody. Answer should be A. Answer should be A. Cannot be B. How can it be B? Cannot be B. Okay? The right answer is A. So let's move on to the next question. In FeCOX, what is the value of X if it follows Sedgwick's effective atomic number rule? Okay. If it follows Sedgwick's effective atomic number rule, what is the value of X? If iron follows Sedgwick's effective atomic number rule, think logically. Think logically. If iron follows Sedgwick's effective atomic number rule, iron's atomic number is 26. It has to become 36. So it needs how many more electrons? It needs How many electrons? It needs 10 electrons. Okay, it needs 10 electrons, and so 10 electrons will come from 5 CO ligands. Okay, the right answer will be C. The right answer will be C. Why would the right answer be B? Vansh Khanna, the right answer will not be B. Okay, I'm very sorry guys, आज मेरी तबीयत थोड़ी ठीक नहीं है. Some days it does happen to everybody. Okay, chalo. Let's move on to the next question. The complex that violates effective atomic number rule. Okay, the complex that violates effective atomic number rule. The complex that violates effective atomic number rule. Which one do you think will violate the effective atomic number rule? Please tell me the answer in the chat box. The right answer is B, potassium ferricyanide. Very good. Potassium ferricyanide formula will be K3FeCN6, and we had identified that the effective atomic number for this is 35. For potassium ferrocyanide, the effective atomic number is 36, K4FeCN6. Okay, K4FeCN6. Clear? Tetracarbonyl nickel is NiCO4, and hexamine cobalt 3 chloride is CONH3 6 Cl3. Okay, CONH3 6 Cl3. All of them follow effective atomic number rule except for potassium ferricyanide. Clear? Ferri means +3. Ferro means +2. So that's the hint. Ferri means +3. Ferro means +2. Now, let's look at this problem. Okay, let's look at this problem. I want to calculate the effective atomic number of the first compound. I want to calculate the effective atomic number for the second compound. How do I do that? Now please do remember that you can see that there are CO ligands. Okay, this is a CO ligand, and there is a CO ligand over here as well. Now this ligand which is present in the middle is known as the CO bridging ligand. Okay, I call it the bridging ligand. Okay, let me just write it better. It is known as the bridging ligand. Now, what is the meaning of bridging ligand? A bridging ligand forms a bridge between two metals, and in doing so, it donates one electron to each metal. The ligand which is present only in connection with one metal donates 2 electrons, but a bridging ligand donates 1 electron per metal. Okay, so bridging ligand donation is 1 electron. Okay, and you can see there is a bond between iron and iron as well. So this bond is known as the metal-metal covalent bond. This accounts for 1 electron per metal. Okay, this accounts for 1 electron per metal. And this accounts for 1 electron per metal. Okay. Now let's understand this. This is not a banana bond. Absolutely not. This is not a banana bond. So let's calculate it for each iron. So I pick the iron on the left hand side. If I pick the iron on the left hand side, so LHS left hand side iron, what is the atomic number? 26. How many terminal CO can you see? So there are 3 terminal CO. Each will donate 2 electrons. Can I say that? There are 3 terminal CO. Each will donate 2 electrons. And there are 3 bridging CO. Each will donate. So 3 bridging CO. Each will donate 1 electron. And there is a metal-metal bond as well. So the metal-metal bond will donate 1 electron. Okay, the metal-metal bond will donate 1 electron. Okay, so that will give you a total value of how much? 26 plus 35, 26 plus 6, that is 32, 32 plus 3, 35, 35 plus 1, that is 36. Understood? It is 36 for left hand side. It will turn out to be 36 for the right hand side as well. Clear? It is 36 for the left hand side. It will turn out to be 35 for the 36 for the right hand side iron as well. Clear? Is that clear? The next one, you can look at cobalt. So let's take the LHS cobalt. LHS cobalt. Cobalt is 27. Okay, cobalt is 27. And I have 1, 2, 3. 3 terminal CO. 3 terminal CO. Understood? 3 terminal CO. Next, I have 2 bridging CO. Each bridging CO will donate 1 electron, and we have a metal-metal bond as well. Can you see? There is a metal-metal bond as well. Okay, so each metal-metal bond will donate 1 electron. This will make the effective atomic number 27 plus 6, that will become 33. 33 plus 2, 35. 35 plus 1, 36. So each of them acquires an E.A.N of 36. I hope this is clear to everybody. I hope this is clear to everybody. So even if you are given a complex like this, in which you have certain bridging ligands, certain non-bridging ligands, you should be able to identify this perfectly. Okay, you should be able to identify this perfectly. Okay. Man, this is not corona. I suffer from allergies. People who are my students from regular sessions, they know that I suffer from allergies on a regular basis. Okay, on a regular basis. Now there is a homework question for everybody. Okay, there's a homework question for everybody. The homework question is this. See, if I have to name this compound, I will name it in a very different way. I will have to use the terminology mu. But right now let's not get into that. Okay, I will have to use it. There is a nomenclature of bridging complexes, but let's not get into that. We will do that later when we do the revision for this topic for just before the mains examination. So let's take a homework question. The question is this. You have Mn2CO10. You have Mn2CO10. Question is number of metal bonds if it follows effective atomic number rule. Okay, number of metal bonds if it follows the effective atomic number rule. That is the question for today. Okay, that is the question for today. Sir, is it easy to crack JEE? No, man. It's not. It's definitely not easy. If it would have been easy, everybody would have cracked it easily. You need to get into the top 10,000 students among 9 or 10 lakh students which appear JEE every year. That's definitely not easy. Okay, it's definitely not easy. Clear? So this is the homework question for today. Please write the answers in the comment section and I will take your name in the next class. So in tomorrow's class, please do join because we'll start with a new topic which is known as crystal field theory. We'll start with crystal field theory, which is one of the most important bonding theories governing the nature of complexes. So crystal field theory will start and then we'll go on to valence bond theory. So until now we have done Werner's theory, nomenclature, effective atomic number rule, and next class we'll start with crystal field theory. I hope you have enjoyed today's class except for my sneezing. Yeah, man. Okay, so still how many more classes? But let's not focus on the number of classes. Let's focus on doing things perfectly. Okay, you should be able to solve questions after every class, and that is my objective. Okay, so let's wind up today, and I hope you have enjoyed today's session. Please do answer this in the comment section of this video. Also, please do join me tomorrow for learning a very, very beautiful bonding theory which is known as crystal field theory. Clear? Chaliye. Bye bye guys, and in case you have any doubts, please do message at saurav.goswami@vedantu.com. Okay, chalo. Bye bye guys. Have a lovely time.